So let's start. I just wanted to just add a couple comments, since Otto was asked, what is mechanistic, what is not mechanistic. And so I want to give you, it just occurred to me to give you a very simple example what I mean by mechanistic. It's a physics example so that you understand. So, everything depends. Okay, you have some questions and you want to understand what is a mechanistic basis. But the key aspect is that what are the scales of the process you're talking about. So this is the example I want to, so they make it clear. Imagine that you're looking at an electron moving in a crystal. And so the electron, and there is an electric field that is pushing this electron. And the electron, as it moves, of course, is interacting with the crystal, the actual substrate. Now, the crystal, we know, is made out of atoms and so on. Now, if you want to represent, modeling, the movement of this electron, and then people have studied over many years, and what they represent, they don't care about the substructure, which is all these atoms and the interaction between electrons and nuclei. They just couple the movement of the electrons due to the electric field to the vibration of the crystal. So notice, we all know that there are atoms in there, which is, if you want, it's an underlying level which create this crystal. But this is fantastic. So in order to represent precisely how the electron moves, you completely forget. And it's not simply because it's unfeasible to do it. If you would go after and try to determine how it comes about because of the structure due to the electronic forces between electron and nuclei, you'll be even wrong. So the scale that you're looking at things is not the scale of the nuclei and the electron distance from the nuclei. You're talking about the movement on a crystal. And what becomes important there, therefore, is some representative movement of the crystal and the electrons, not the nuclei. So it all depends on scales. Does it help? So that would be studying that electrons moving, coupling with the vibration of the crystal. That's a mechanistic aspect to understand the movement of the electron. You don't need to go deeper. You'll be wrong if you go deeper, besides being unfeasible. But is it clear? Okay. So since Otto, answer to you, they're talking about flight speed. Well, if that's the pattern that you're looking at, the speed, in that case, is mechanistic. Even, of course, there is other things which are underneath. Well, so this is just occurred to me when I was listening to Otto, so I wanted to say. So beyond statistics, so what I want to tell you is that if one is interested in predictions, and of course you have to be careful a bit in prediction when you talk about biology, it's not like a physics experiment, but to understand in a quantitative way, therefore expect outcome even from experiments you have not performed, then you need some mathematical model. So, and then this is, in our case, we are interested when spatial and temporal scales can be varied, or parameter values of a model that works can be varied. What happens in a different system, but which undergoes the same kind of processes. So that's that's why we think about mathematical models. So there are two equivalent formulations. One is the Langevin description. I'm not going to talk at all about that. And there is the probability description. And of course, I'm going to talk to you about this. Well, not simply because I've worked more in that context, but I think there is much of an intuition that can be built. Langevin description, if you want, it's based about writing stochastic differential equation and then studying the noise associated with it. It's a stochastic differential equation. There's noise associated with it. And then you worry about, if you change the type of noise, what is the output? So probability description, on the other hand, you put all these trajectories, hypothetical, random trajectories of a process, and you create this probability description. So that's what we are going to discuss about. And so they will talk about probability density function and what is the advantage, why I find it very convenient to use. I just stated here. As you have boundary conditions, and I'm going to talk a lot about this bounded movement, then it's the easiest way to implement them if you have a probability density function description rather than Langevin description. So this is the only slide I'm going to show you. Well, I have others just to see if I do the right math. And so now we're going to really work hard. So you just put your, nobody has sleeves probably, but just put your sleeves up. And now we're going to do math. And then will be an exercise this afternoon to see if you have understood. So let's talk about random walks. and let's talk about continuous time and discrete space. So imagine that I want, so so here today I'll just do 1D, then we worry about 2D next. So imagine you have a lattice. A distance is A, characteristic distance there is A, so it's a unit of length. And then imagine that you want to represent, I mean, would you allow me if I put an individual rather than an animal here? So, and he's moving, it's an animal, but let me just put, because I don't know which one I should draw, but so, a wild animal, let's say. So, if I put this arrow, imagine that I'm there, and now I have some chance of moving right or left. So let's call this one a rate. So it's a rate of moving left or right, which is equal in the simplest case. And then I want to describe such a process with a probability description. So what I would do, I would just write, or is it big enough? Someone, or do you think, who is up? Can you read? Yeah. So I would just write the probability, the evolution of the probability of being, I put a sub-index n, which is here, n, and then puts n minus 1, n plus 1, n plus 2, and so on. So n runs from minus infinity to plus infinity. And then it's, of course, it's a probability as a function of time. We want to change how the probability of being at position n would change as a function of time. So it's a differential equation. And so if you think about writing that process, so you have to think about what is the chance of moving if you have a rate f. Remember that you also have a rate f, if it's all is equal, of doing this. So if you are at position n plus 1, if you're there, then the rate f, if everything is symmetric, to go into site n, and from n minus 1 to go into site n. So what would you have? You would have the rate f, and notice this is differential with respect to time, so the better be the rate here, so that we can match the units. And then, so if I want to talk about the probability of being at n plus 1 to be there, so I want something that would increase, you know, if I have a positive term here, I would increase my probability of being at n. Okay? So if I have describing the, remember this is describing how the probability of being at n varies over time. If I'm at n plus 1, then I will have a positive input to that differential equation, because I will increase the chance the Pn, so Pn will tend to increase. So the derivative will have a positive sign. So there will be, if you want, just put a plus sign, but then I need to be at n plus 1 for that to happen. So it's f multiplied by p n plus 1 t. Is that clear? So in some sense, you know, when I write a general object, dy dt over dt is equal to some positive constant plus y of t, let me emphasize the plus. So this y of t keeps increasing as function of y. No? So that's what I'm trying to do here. Now, so there is a sub-index n, because we are talking about also space here. Otherwise, you would have something just like this. So this is an input to n, so that will make, if you are here, there will be, with the rate f, there will be an increase of the probability of being there, because you are at n plus 1. But you can also see that there is also the input n minus 1. So therefore, what would you expect to have here? Plus f,
Pn minus 1.
Very good, Pn minus 1, t. So that makes Pn increase over time. And what about these two arrows? Then you have a minus, because this is going out of site n. So there will be a minus f, but notice that f is out, but there is another f here, so you better have 2f. And then you need to be at site n for that to happen. So you multiply by Pn n t. Is it clear? And this is for, now, notice that I've written for a site n. I didn't specify what that site n is. I could talk about the one which is down here. I mean, that would be number n equal 275. And then will be linked to the site 276, 274. So n is running from minus infinity to plus infinity. So this is what is called, this is a fundamental equation in statistical physics, if you want. It's a gain-loss equation. It's a very simple equation. It's a gain-loss equation. So Pn gains because of this input and lose because of that. So imagine if we had a random walk which, rather than being symmetric, would have some chance of going more to the right or left. So then a simple way to do it is that you would modify this f by putting some probability between 0 and 1. So let's say we can put all the one that you go to the right, they have a delta, which is, let's say, it's a value between, well, and 1. And then, so let me just put n minus 1. So this one would also be delta. And this one would be 1 minus delta. So you can ask the question, why is it that you put 1 minus delta and delta? And I'm going to show you. You want to conserve probability. So in this case, let's try to do in the simpler case that this is a probability equation. So probability has to be conserved over time. So it means that, you know, sum over n, p of nt, better be 1. So the chance of finding the walker at any of the n sites is 1. You don't know precisely where, maybe, but it has to be 1. So in this case, you know, n runs from minus infinity to plus infinity, if you want. And notice that I'm going to show you that the way you have built, this is built, is automatically satisfied. And the way you do it, oh, there's something behind here. The way you do it is just you have an equation which is derived with respect to time. Notice that this, if I sum the entire equation here to the left, to the right over m, then n does not depend on time. So I can sum and then I put in front of the derivative. So then it's Pn of t. And then I have to sum also this, the right hand side. So I have f sum over n, and let me not put from what to what, it's implicit, n plus 1 of t plus f sum over n, Pn minus 1, t plus minus 2f sum over n, Pnt. Now, you have to be careful because now we are summing n and you have Pn plus 1, and here we have Pn minus 1. But what happens here, remember that here we are going from minus infinity to plus infinity. So if I sum Pn plus 1 or Pn, it doesn't matter. I can just rename this one because you have an infinite number of those terms. So this is the same as this, and this is the same as this. Is it clear? It's an infinite number. If it was a finite, no. But just because it's infinite. So this is the symmetry of the problem. Therefore, what do I get from here to there? So I get the sum over n. So this is common to the three of them, which is Pn of t. And then I sum f plus f minus 2f, 0. So therefore it's 0. Remember, so I just sum this. I sum over n this left equation, and I have to sum over this right equation. So I have the derivative of this quantity, which is equal to f, the sum of Pn plus 1 over n, which is the same as this one for symmetry, and then it's the same as this one. So I take this one, which is common term of the 3, and then I sum f plus f minus 2f. So I get a 0. So 0 multiplied by that is 0. That means that this quantity, which is the derivative of that quantity here, is constant. The derivative is 0, so therefore the sum is constant. And then just to be intelligent, you just make it 1 rather than a generic number. Huh?
Why is Pn plus 1?
So the point is that this one. So sum over n from minus infinity to plus infinity of Pn plus 1. So if I'm summing an infinite number of terms here, and if I start considering my origin being 0 or 1, since it's an infinite number of terms, like is this, it doesn't matter, no? So I mean, formally, if you want, I can just rename this. Let me call n plus 1 n prime. So if you want formally, so you call n prime, and then you sum over n prime, and now since you were summing from n, then it's n prime minus 1, no? From minus infinity to plus infinity. And now you have a p n prime t. Now, you don't mind if I put this minus 1 on the right-hand side, no? So what happens minus infinity to plus 1, and plus 1 is still minus infinity. Huh? In the case that n is infinite, so we are talking about the simplest case for the moment. I mean, we'll worry about bounded motion, I mean, tomorrow, the day after tomorrow, so. But this is just formally, it's clear? So, so that, I mean, if you, now you have, so at the end here, what you have the sum over n prime from minus infinity to plus infinity of p of n prime t, and n prime is a dummy index, so I can call it n or n double prime, doesn't matter. So which is the same as what you find here. And therefore, so this is conserved. Now if you add this term here, let's now rewrite this equation, this master, gain-loss equation, if you don't want to master. So we have Pn plus 1, which had f1 minus delta now. So the Pn into n, so there is a 1 minus delta here in front. And then, what about this? From n minus 1, there is a f delta. And then minus 2f. So notice that we have to do, so let's do carefully, and then you see you get the same stuff. But so you have minus, remember it's a minus, f1 minus delta, and then Pn, because it was this arrow, plus, actually minus, well, plus here, minus here, f delta Pnt again, which is this one. And so, I mean, if you see that there is a plus f delta minus f delta, so let me just rewrite it. It was before, so it becomes the same as before. So this term is minus 2f delta f Pn of t again. And now, let me not do it, I just tell you that. Now do the same exercise as before, sum over all the ends, this side and that side, and then you'll see that, okay, this, you have minus 2f, sum of Pn is the same, and when you sum these, you do the same trick, and you know there is a minus and there is a plus. So that part goes, and I'm missing a factor of 2.
The first and the third and the second and the fourth.
Yeah, I'm missing a factor of 2, yes, exactly.
It's not minus 2, it's just minus f.
Where is it? Sorry, where is it, guys?
At the top you have 2, but you shouldn't have.
Yeah.
Oh, yes, sorry. Yeah, actually, you know, I know I have this factor 2 because I should, when I input this, I should put, to make it clear, I should put that, you do like this because of a reason that you become clear later. Okay, but anyway, it's just a renaming f. Okay, so that's, and so that again, you get 0, the derivative, so, and then again, you conserve probability. So this is just to tell you why, if you want to put a bias with a delta, which is a value between 0 and 1, you're going to have to do it like this. All clear? Now, first thing out of this equation, this random walk equation, continuous time, is let's calculate moments. We don't have to solve the equation. If you solve it, I mean, you can solve the equation. You have I Bessel function. It's complicated. We are clever, so we don't solve the equation. We just want to understand the moments of that equation. And so similarly, you were seeing me before doing. So, what are the moments? Well, remember that I told you yesterday, when the variable is continuous, you have a probability function. You do that, no? And then there was the nth moment. So that was the nth moment. Nth moment of p, no? Now it's discrete. So instead of having an integral, what are we going to have? A series, just because they are discrete values. So let's calculate the first moment of this equation. I should not, well, we have it there. Huh? You should have a blackboard here. Okay, so you all see here. So the first moment is that I take that equation, and remember there is a Pnt here. So first moment, remember this is y, n is equal 1, no? So let me multiply by n on the left, and also on the right, we'll do it, and then sum over n. So that's the derivative of the first moment. You agree? And so what happens on the left-hand side, we have f sum over n Pn plus 1 t. Well, let me just do it in the simple case. So plus f without the delta. F Pn sum over n Pn minus 1 t minus 2f sum over n Pnt. Now, of course, you can see that there's a derivative of this quantity, which is the first moment. So it's going to be a function of time. So let's put a symbol. Mathematicians use different symbols. Statistical physicists use other symbols. So I'm going to allow me to use statistical physics symbols. Sorry, also. So that's n average. So the average means just summing over the index n. So, but of course it depends on t. So better depend on t. So I can write this as a derivative of the mean. That is equal to. And now you wonder, oh, but we don't have something that depends just on average n here. No, we do. But now you have to be careful. So this one is clearly the same as that. But what happens to this term? Now some magic. So notice there is an n here. Would you allow me to sum n and subtract 1? So sum 1 and subtract 1? I guess you do, no? And then you come here. You allow me to subtract 1 and add 1. So it's the same object I've written before. And then what happens here is that you have f. And here I have sum over n plus 1. So I take the first n plus 1 because I have a Pn plus 1 here. But then remember, I have to remember that there is minus 1. So it's minus f sum over n. And then I have Pn plus 1. So this is just from this first term. You see? So n plus 1, I put it together with this. So I get the sum. And then I have to remember that I put the minus 1. So, but then I have sum over n, sum minus f sum over n of Pn plus 1. So plus over here is similar, but I'm interested in n minus 1 to isolate that. So I have f sum over n minus 1 multiplied by Pn minus 1 t, and then I have this plus. What happened to the other blackboards here? So plus, remember this is a plus sign, f sum over n, and now it's Pn minus 1 t. And this is, I don't have to do anything here, it's the same as that. So we have this first term, and now what do we have here? This is the derivative of that is equal to this quantity here. What is it, this quantity? As before, if I call n plus 1 n prime, and I sum over n prime, it's the same. And here, it's obviously here is the same also. So you have f plus f, so it's 2f, 2f average n, because of these two terms. And now notice that I have this term here, which is the sum over Pn. It doesn't matter, n minus 1. And this is a plus and this is a minus. So this one goes with that. And then magically, what happens is that you have 2f sum over n, and then minus 2f average n. 0. Well, of course, you could have expected that from the beginning, no? So average n of t is constant, because that's a derivative, which is 0, so it's constant. And whatever is the initial value remains that. So let's put it 0 just to make it simple. And of course, this is the random walk is symmetric. So if you measure the mean with respect to some origin, if you want, here, if you start here and then you calculate the mean, it's equally likely to go a bit on the right, a bit on the left. And over time, if you put all the possible trajectory together, you get exactly 0. I mean, if you do on the computer, we'll learn how to do on the computer, you see that as you increase the number of these trajectories that you do the average over, then you get closer and closer to 0. So the noise gets smaller and smaller. So mathematically, it's going to be 0 when you have an infinite number of trajectories. All clear? Oh, what time is it?
20 minutes. Like
10 minutes? 10 minutes, yeah. So now, the more important thing is that we are going to calculate the second moment. And then still in the case, I don't have time to, I mean, I'll show you the one for the delta maybe this afternoon, when delta is, let's see, a big blackboard here. Let me do it here. So now we are interested in the second moment, no, which is the mean square displacement. I've talked to you about this yesterday a lot. So what is a second moment? Yeah, let's define it as average of n squared over time, which is sum over n squared Pn of t. Now, of course, you understand now what you need to do. You just multiply by n squared to the left and right, and you sum over n. So if you do it, you get the derivative of time n squared of t. And then, so this is for delta, which is not there. So then you get f sum over n squared Pn plus 1 t plus f sum over n squared Pn minus 1 t minus 2f sum over n squared Pn t. Horrible writing. Huh? So, and now of course now probably you know what do you think I will do in order to determine the actual derivative, the evolution equation for the, well, I shouldn't use evolution with biology, but the time dependence of the differential equation. So, well, as before, no, I sum plus 1 and I subtract minus 1. And then I separate terms. I don't know, do you want me to do it, or it's enough to tell you the result?
Believing it will be linear on f.
Very good. So, should I do it? Should I not do it? No. No, okay. So what you get? Homework. Okay, that's right. Good homework. So what you get 2f. So, which means that the derivative of the mean square displacement over time is equal to 2f, and therefore n squared of t we know how to integrate this equation, no? If you want to write n squared of t, you all know? Yeah, I mean, but then you have an initial condition. So you. So that becomes n squared of 0 plus 2ft. Now let's try to put units, because here I'm not just talking about numbers. You remember there was a value here. So I have n squared, I wanted this, the average distance squared. So let me multiply that equation by a squared. So I have n squared, a squared. Well, let me just put here, a squared, n squared, t. So this is your MSD. Now in the right unit. And so this is equal to, well, okay, there is, let's suppose this is 0. Let me not rewrite that. And then it's 2f a squared t. Okay, no, just. So, I mean, also was talking about sigma squared tau, no? So this is, tau is the inverse of 1 over f. So tau is 1 over f. Huh? So, and sigma squared in this case is a squared. So that's in discrete space, continuous time. So we've just found out that the mean square displacement increases linearly. When delta, when there is no drift, we'll do it this afternoon with a drift. So then you have something that, you know, just linear. And so this afternoon, I have to talk to Angel because maybe he was planning already to do this kind of, I want to create this, both to see this linearity on the computer. And which means, not solve, I mean, you have solved the equation in some, we have solved the equation for the mean squared, but to putting together trajectory, no? You put together all the trajectories, you sum over these trajectories, and I'll tell you, how to do it, and then we get them. So,
what's the slope?
Well, the slope is exactly, what is the slope? What is this fa squared? Now, we all, I mean, you've heard many people talking about diffusion constant. So what is a diffusion constant? Well, we'll go to the continuous limit, maybe tomorrow, I think. But I can tell you, if you do this limit, f, this is a mathematical limit, f goes to infinity, a goes to 0, such that fa squared is a constant, and you call that the diffusion constant. Then you have your continuous version of the mean square displacement, which is 2 dt in 1d. If it's 2 dimensional, it would be 4 dt, because you have also the other. So what does it mean when you do this limit? Well, you know, a becoming 0, so this is getting closer and closer to the other. So the number of those points, you know, you're crunching everything, and and since they're becoming infinitesimally next to each other, then you better make the f being very large, okay? But now, you may ask the question, which, but why on earth fa squared, no? So this is just dimensional analysis. So when you go from discrete to continuous version, there is not much, I mean, there is one limit that gives you the right answer, and there is not much intuition about doing it. You just have to get the right limit that you know what the corresponding continuous version is. So that's, you know, dimensionality that tells you that this is what it should be. Now, if you don't get the right continuum limit, then it means you've not taken the right limit. So I guess 10 minutes are gone, probably. Is it all clear?
So what is the slope?
What do you mean, what is the slope?
Write down. Yeah.
Oh, the slope you want to know. So it's 2, well, this is in 1D is 2D, no? So in 2D is 4D. So if you have, oh, please. No, if you have data, and if you have one way, if you want to characterize, for example, animals, and you have, you know, nice resolution, then you can just take the initial position and just check. You know, imagine you have many different animals of the same species, and you assume that the statistics is similar in the same habitat. And even if they start in different initial position, then you just follow the different ones, and you reconstruct this. I'll tell you how to do it. And you reconstruct this from the data. There is a time window averaging technique that you have to use. And this, I'll explain you why you can use that in the context of what you've learned today. And so then you get the slope, and then you compute, and then you have a quantity that characterizes the diffusion constant of the animal, for example.
You
Yes?
know what's in the y-axis of this graph?
Oh, sorry, this is the MSD, sorry. Ask that, I forget. You know, my teachers always told me, you know, when I was in Italy, said, well, every time you put axes and you don't put the symbol, what they represent, well, at the time was 1.000 lire, so it's half a euro. But I lost so many of these half euros. But anyway, so tell me how many.
I missed what is A.
Oh, A is is here. It's a distance, so it may not.
Distance between n and n plus 1.
Two sides. It's a distance. It's a characteristic distance of your side, of your lattice system. Now, for example, I don't know what you heard yesterday. The A, because remember I was talking about a lattice there. That characteristic distance, given a species, is the distance over which they deposit scent. You know, some animals, they really do it every 50 meters. Some others, you know, in that context would represent something biological. This is more general now. We haven't said much about. Is all clear? You said yes. Good. No, yesterday you scared me. So, but is it all clear?
Yeah.
Now, one suggestion.
Now you explain what MSD is. So.
Yeah, but one suggestion is that play around, try to do the exercise with delta. Because if you don't, you know, math is like this. You may understand everything, but if you don't really try to do a simple thing, try to even repeat what I've done, then you forget. Maybe not in 2-3 days, but in a week, I can tell you.
Squared in time. Squared in time.
This is squared. No. So try to do the delta. No, but no, we all go to lunch. No, so the delta I'll do it myself to show you it becomes t squared. The delta. When you have delta, which is a drift, I'll show you it becomes t squared. So try to do, I don't know, try to do the n squared, the one we did here, no? So just try sum and subtract plus and minus 1 and separate terms and try to see what happens. So I'll see you, whatever, in an hour, no? More or less. An hour.
1:30 we'll meet at the computer room.
Oh, at the computer room.
We have a board though.
You need
Okay, perfect. No, that's it. Yeah, it's probably they are farther away, but
I think they can see. Yeah, I think it would be easier.
yes, please.